yourself, but only a couple of things. So we're looking at first part using set and interval notation. So on your worksheet here, what I've said, this relates to the work you're going to do in a second, exercise 2C, page 62. If you want to open it now, it's not a problem if you don't. Basically, a few things. When we deal with Venn diagrams, we're dealing with sets of numbers, and you put those numbers into certain regions within the Venn diagram. We've been looking at that. But before you can do that, you need to be told which numbers we're dealing with, right? So you'll be given a set of numbers written in a different notation, so using set notation. And the first sign of set notation are the fancy brackets, the curly brackets, all right? So when you've got curly brackets, that just says to you, right, this is the set of numbers. So whatever falls within those curly brackets, those are the numbers that you're going to be using, right? So that would be what for the Venn diagram. If I just gave you one and went, this is all the numbers, that would be which set for the Venn diagram. You saying? Which set? Universal, there you go. Right, so if I gave you a curly set of brackets and said these are all the numbers for the Venn diagram, you would know that that would be a universal set. So then I may as well say to you, set A is these, are these numbers, and I would put another set of curly brackets. Okay. Now, I've written a little note here. The brackets could have just a list of numbers in 2, 3, 4, 5, 6, and you'll see that when you look at the exercise. So it could just have numbers, okay, but it could also have interval notation. Now I'm pretty sure you've seen this before, okay. So it could either have just a list of numbers or it can have interval notation. So the more or less than, or the more and equal to, or less than or equal to. You recognise that notation? Bless you. Are you happy with that? Yeah. Or would you like to go through those at all? No? Okay. So what I've done here is I've written an example of how set notation can be used with the curly brackets and some information. So it's on your sheet, but let's just go through. So to start with, curly brackets, the set. We've got an X, it could be another letter, depending on what we're talking about. But what we're saying is X with then just a straight line. And all that means is X is taken from a set where, then you go into the next bit, X is between -2 and 1, inclusive. Why have I written the inclusive bit? There? Yeah, because it's the and equal to, so it's between -2 and 1, including -2 and 1. Alright? Then we've got this extra little bit here, which says X is also an element of this Z with a double line in the middle. And Z represents the set of integers. Okay? Does that make sense? Why is it Z? I don't know actually. It just is.
What is that line next to the X? Does that have a purpose of anything?
This line, that bit,
yeah,
it's just to say separate it from the interval, that's all. And it's just saying X is taken from a set where put a line, that means take that bit. It's just part of the sentence. Okay. Now what we can do, and you can maybe write this under the space as well, we can actually be more specific now with which numbers I can actually use. So if I say X has to be integers between -2 and 1, which integers are those? And do you know what integers are? Pardon? Whole numbers, yeah? So what's the first whole number I could use? -2. So in my squiggly brackets I could put -2. The next one would be minus 1, 0, 1, 2. Is that right?
Yeah. No.
No, because it has to stop at 1. So, oh. So, actually all of this could be written just like this. So this is the set notation for just the list of numbers that I said. And this is the set but with interval notation. Now both of those mean the same thing. Okay. Now you might say, but why bother writing all of that when I could just list those 4 numbers? But it's not always just going to be minus 2 to 1, it might be more numbers. Well, that's just saying, so x has to be between minus 2 and 1. But if I had just that, minus 2 and 1, how many numbers are there between minus 2 and 1?
4.
How many?
There's a lot.
There's actually infinite number of numbers between minus 2 and 1. Close enough, billions. Because you can go to any number of decimal places. Keep going. So, if I only wrote x was between minus 2 and 1, I could not write the numbers. So what they've given you is another piece of information, a second piece of information, which states, well, out of those infinite number of numbers between minus 2 and 1, we only want to use the integers. So x is an element of integers, so you can only pick from integers. Okay? So, does that make sense?
No. Can you say this much easier? I get the whole those parts. I'm confused. What are you talking about with the minus 2 and the
Right, so if I look at this, x has got to be an integer between minus 2 and 1.
So it can't be a decimal.
So it can't be decimals. Yeah.
What do you mean by x is an element of z?
That's the x is an element of. So remember when we talked Venn diagrams, so you are an element of this maths group because you're in the group. Okay. So we're saying x is a number that is an integer. That's all we're saying, right? It's just I've used the official language, but we just basically that is x is an integer, right? And if you look further down your page, you'll see that there are other letters for different sets of numbers. So yeah, got a question?
No, I just saw it.
All right. Okay. So what I said there was that if x is only an integer between minus 2 and 1, well, which numbers can that be? Minus 2, minus 1, 0, 1. So this bit and this bit are the same. Okay? It's just written in a different way. So this is the whole long-winded official way of writing it, but this is the numbers. All right? So if I wanted to put those numbers in a Venn diagram, I'd know what the numbers are. Alright. So obviously, this interval notation could change. You might be given a question that's in interval notation. It might just be in set notation, whichever one. Now, let's have a look at different number sets. So I've left a space there for you to write some examples. Right, so N stands for natural numbers. Any idea what numbers might be natural numbers?
1.
Yeah.
11.
11, 2,
13.
13. There's another name for them. Counting numbers. So, that would mean natural numbers will not include what? Decimals, definitely, and also, pardon? Fractions, that's decimals. Fractions, decimals, but it won't include negatives. Because how many sheep are outside your window? -5. What does that mean? Yeah? So you think of the natural numbers were the first numbers that came about. Yeah, because people did say, how many goats would you like to swap your daughter for? You know, 5 goats. You know, back in medieval, you wouldn't do that now. You know, How many grains of corn have you picked up? 150, you know, the counting numbers. Yeah? Ears of corn, I don't know, whatever. So the natural numbers are the counting numbers. So you can fill in a few, right, yourself. So natural numbers, hopefully you've got starting at 0, 1, 2, 3, and so on. Well, you need to know that 0's in it. Okay? No, that's the web discussion. Okay. Integers. Okay? Now integers, you might think same thing as counting numbers, but what is extra? Negatives. So we must have negatives in there as well. Alright, going on both directions up to infinity. Okay. So the only difference between natural numbers and integers is negatives. Okay. By the way, you can have extra signs, like if I put a little plus by the Z, that would say only positive integers. Okay, is 0 a positive integer?
Yes. No.
Yes. Yes, no, maybe. Coming along.
Yes.
It's not, because it's not positive. It's also not negative. It doesn't belong.
It's
Neutral. It's the Switzerland of numbers. Right, rational numbers then.
2.2. Yeah.
That's not rational.
Irrational.
That's irrational. The next one. Right, come on. Yes. Focus. Rational numbers, anyone know what they are? Yeah.
Is it like a number, like you know how you have recurring decimals? It's a non-recurring number.
Close, that's the next one.
Okay.
Okay? Rational numbers, the definition for a rational number is any number that can be written as a fraction.
That's like 1/4.
A quarter, a half. But actually, all integers are rational because 2 can be expressed as a fraction. 2 over 1, 4 over 2, 6 over 3, fine. There are only certain numbers that can't be expressed as a fraction, which is what I think you were saying, which is those numbers that are non-recurring, non-terminating decimals. Okay? But what about recurring decimals, like 0.3333? Can that be expressed as a fraction?
Yes.
What is it?
1/3.
1/3. So 0.3 recurring is 1/3. 0.6 recurring is 2/3. 0.712571257125 is a different fraction, okay? Which we will learn how to do, by the way. We will learn how to convert them. But just because they're not recurring, just because they're not whole numbers, they are recurring decimals, doesn't mean they're irrational. So rational numbers, what we would write, we might just write numbers that can be expressed as a fraction. Now it's probably more interesting then, if that's everything other than irrational, which numbers are irrational? The ones that are non-terminating and non-recurring. The most famous one would be
Pi.
pi.
Really?
Pi is an irrational number. We watched the video. Have you seen it at all? The boy with the incredible brain.
Yes.
Some guy, he apparently sees numbers as emotions and colours and images and shapes. So when he remembers pi, to however many decimal places, he actually imagines like a landscape and he walks around and just looks at colours and shapes and things, and that's how he knows what the number is. He just sees it. Doesn't have to work anything out. Now he did a memory feat where he could remember. Do you remember when you did that memorising the numbers that came up and you got stuck at about 8? He, 6. He did pi to, what was it, 250,000 decimal places. It took him 5.5 hours to recite it. Why you want to know that? Other ones then, one from your card. Square root of 2, yeah. Square root of 2 was irrational. Basically a square root of any prime number. And then actually, as you have done with surds, most square roots can be expressed as something times the square root of a prime number. So that would suggest the only square roots that are not irrational are square roots of square numbers. Yeah. There are others like the number E.
There's a number E.
Like pi, it's given a letter. Yeah. Anyone heard of the golden ratio and all that?
I've heard of the golden rule.
Golden ratios this is a ratio that appears in nature. So you look at you find a ratio between bacteria that divide and reproduce. You look at the ratio between the size of flower petals and things like that. If you find a ratio, it comes out as pretty close to one number all the time, and that number is a non-recurring decimal, so we give it a letter E.
What did he say about the
So the sign, by the way, Q is for rational. Q with a little star, or sometimes you see a dash instead. Basically, Q with something up there would mean irrational. Right? Actually, what we ought to potentially, I know you can't rub yours out, but this sign you'll see in a bit, hopefully this lesson. And finally, real numbers. You'll notice we're going in a kind of order here. Real numbers are all numbers on a number line, which is basically all numbers. All irrational, rational, all numbers. Well, what it suggests though, that if there are real numbers, there must be
fake numbers.
Fake numbers, like what you know, but they're not called fake, they're actually called, someone said it?
Oh, imaginary.
Imaginary numbers, you say? And imaginary numbers, do you know the letter to go with imaginary numbers? I, yeah, you've probably seen that.
No, just guess.
I, it is I. Right, you don't have to do this in your course. I haven't written it because it's just for interest. I is the square root of -1. Tell me why that is not a real number.
Because you can't square root of minus
Because you can't square root a minus number, but funnily enough, without that, there's an awful lot of maths, very high level maths, that can't be done. So we say it doesn't exist, but actually we need it. Yeah. Alright. So a lot of engineering and things like that needs the square root of minus, and we get complex numbers, imaginary numbers. But we don't have to worry about that. But it just explains why we have real numbers if that's all the numbers. But okay, just to finish this off quickly then, so that you can get on with some exercise. You got a question?
Yes. What did you say was the connection between irrational numbers and square numbers?
Oh, so if we square root a prime number, we get an irrational number. But most numbers, when you square root, remember your surds work, you can simplify them to be something times the square root of a prime number. So really, the square roots of square numbers are the only ones that get whole numbers up. Okay, just to finish this off, showing these number sets on number lines. So I've got a number line here. I've got some dots on a line. Now I'm going to add some numbers like, let's say, -3, -2, -1, 0, 1, 2, 3. This would represent the set -3, -2, -1, 0, 1, 2, 3. That's all that means. But you can only pick those numbers, right? Wherever we start, you need to add it. Okay. Now these two are different. So, for instance, this one I might stick something like that. If I were to write my full set notation, I would say x belongs to, and I would say what? X must be greater than or equal to 5. Okay, and that's it. There is, I could say x is an element of.
We have to do the fancy brackets like that?
Yeah.
Yes. Didn't I tell you? We can't do regular brackets?
No, Sam, that's not how life works.
I can.
I can't do them very well either.
Put ease.
I can only do a regular side one.
Yeah. And also, I can do 3 of them perfectly well, and then the 4th one will be like, right.
Three's always.
Can I just ask, why do you think it's
Oh, so that's not X1 then X0.
yeah, that's an X with the line, yeah. What do you think that and equal to? How do you think that's represented? Well, that's represented by the fact that the circle is filled in. All right.
Yes, I remember.
Remember that.
Integers.
And the x is an element of real numbers is because the arrow, there's no gaps, not like the dots. This is,
Oh,
yeah. So what would you think this final one was? I'm going to let you do what you think the final one would be. Right, so whatever numbers you pick, so let's say I'm going to pick minus 18 and 263, okay? Doesn't matter, does it? It's 2 numbers. So I can say, and this is my tip, so I'm going to write the minus 18, and I always write my arrows that way round, because the arrow, the small end, the point points to the smaller number. So we read small to big, left to right. So it makes sense that small to big. So if I put my arrows always that way round, okay, put the x in the middle, and I put minus 18 to 263, but I've got to be aware that that one's filled in, so therefore I must have the and equal to, right? So I've got x can be anything between minus 18 and 263. There's no limits to that because I have a solid line. There's no dots like this one. So a solid line, even whether it's an arrow, so there's only one limit, or just a line segment, meaning 2 limits, that means we have to say that x is an element of,
Integers.
not integers, because that would lead to dots. It can be anything, so real numbers. And then I finish off that.
I have a question.
Yeah.
What did the line of the arrow mean?
This up here. So this basically means the arrow means, I could say it like this: x has to be greater than or equal to 5, but less than, which doesn't make any sense actually when I write the next thing, which is this switches back on. Infinity.
That's really
Can you see
tough me off.
like
So basically I would say x has to be greater than 5 and goes on forever. So how many numbers are greater than 5?
A lot.
Infinite.
anything?
Yeah. If you give me a number that's greater than 5, I can give you one bigger than your number. Simple as that.
5.1.
Okay. So we have an arrow that suggests there is no upper limit. Okay. The arrow could go the other way if we wanted, but then the symbol here would go the other way around. Okay.
But you put
Wait,
Go on, what?
Put the arrow that way and then you put it
Yeah,
that way.
I know that kind of goes against what I have said. So let's have a look. If I were to write it like, if I always stick my arrows the right way, so basically, if I do that and equal to, I know that 5 is the lower limit because the arrow goes above it. So I could put 5 that side and then X. Then I follow my own rule.
So anything greater than 5.
Anything greater than 5. Does that make more sense?
So mine's point 6 is their back and then it's going up or down.
Yeah. Okay. Is that making sense to you? Right, can I get you then, like it says at the top of the sheet, have a look at page 62 in your textbook. Okay.
Oh, my back's hurting.